Hello everyone, today we're going to be talking about limits and continuity. This is our basic formula. It's read, the limit as x approaches c of f of x. So what our answer should be is a numeric value. Whatever the y value is of the point where c and our f of x graph cross. So this is considered a two-sided limit. A one-sided limit is where we're approaching our c value, but only from one side. It's written with either a subtraction sign or an addition sign behind the c. So in this example, we are looking at the limit of x as it approaches c from the left side, because it is c minus. In this case, it happens to be the same for both. Here's an example where it's not the same. As you can see, we're approaching from the left side, and we ignore the bottom line because there are no values to the left of c. So here we're going to say it's approximately 3. I didn't write anything on the graph here, so I'm just making that up. But it would just be whatever the y value is. But what if this is an addition sign? So if it's an addition sign, we'll approach the c from the right side. And here we're going to say it's approximately -2. Again, ignoring the top part because there is nothing. What about f of c? That would mean wherever the actual value of c is, what is our numeric value? So whatever point it is. Here it happens to be 3. So now we're going to move on to continuity. This is our basic formula. You would read it as the limit as x approaches c from the left side of f of x is equal to f of c is equal to the limit as x approaches c from the right side of f of x. Now, if and only if all of this is true, is f of f continuous at c. So here's our first example. We start from the left side, going towards the value of c, pretending that this does not cross over the value of c. So here our y value is approaching infinity. It's getting larger and larger. At the actual point of c, there is no value. Therefore we write d and e for does not exist. Here we're going from the right side towards c. Our value is getting larger but getting negative as well. Therefore it is going towards negative infinity. So these values are not all the same. Therefore our graph is not continuous at the point of c. This happens to be an infinite discontinuity. In our next example, we start the same way, going from the left side towards c. Our value at this point is approximately 2. Next, we look at the value at the actual point of c. Again, it's 2. Finally, going from the right side towards c, we can see our value is once again 2. Because all of these values are the same, our graph is continuous at the point of c. In our third example, again we start from the left, going towards c, and we see our value is approximately 2. Now when we're looking for f of c on this, we need to look at the bottom part of the graph, because that's where there is an actual point. When there's an open circle, it means the graph does not actually exist there. So going from the right towards c, once again our value is approximately -3. So two of these values are the same, but 2 is not equal to -3. Therefore this graph is not continuous at c. So here's our final example. So starting the same way as always, because we have c minus, we're going to start from the left side, moving towards c. Our point here is approximately 3. Next, we're going to look at f of c. Here we have 2 open holes. Therefore, there is no point at c. So we write d and e for does not exist. Next, we'll start from the right side, moving towards c. Our point here is approximately -3. These 3 values are not equal to each other. Therefore, our graph is not continuous at c. For help telling these 3 different types of discontinuities apart, without using a graph, click here. That's all for today. Don't forget to subscribe for more math help.